Imagine discovering that, while much of the world argued about the future of energy, China quietly crossed a line that American scientists had labeled unreachable for over 50 years, while the United States celebrated its status as an energy superpower. Chinese engineers were working in silence on a project so radical, so disruptive, that it could render most Western nuclear plants outdated within a single decade. This has nothing to do with ordinary solar panels. Those are already cheap and reliable across most of America. And it's not about wind turbines either. What China built goes far beyond anything seen since the Manhattan Project. It is more powerful, more daring, and more transformative than any energy breakthrough of the modern era. And the roots of this story stretch back much further than you might expect. But before we begin, don't forget to like and subscribe to our channel. Between 1958 and 2006, China completed the construction of the Qinghai-Tibet Railway, also known as the Qingzhang Railway. Today, with more than 600 miles of track above 13,100 feet in elevation, it is the highest railway in the world. Passenger trains now depart from Beijing, Chengdu, Chongqing, Guangzhou, Shanghai, Xining, and Lanzhou and can carry between 800 and 1,000 passengers during peak season. Of course, building something like this was no easy task. There were bottlenecks that engineers had to work around. To begin with, about half of the second section was built over nearly unstable permafrost. In summer, the top layer thaws and the ground turns to mud. The heat from trains passing overhead can melt the permafrost even with small temperature changes. The fragility of the permafrost is the main problem. In areas where the permafrost is not so fragile, an embankment of large rocks is enough. But in the most delicate regions, the track has to be elevated like a bridge. Engineers solved this by building elevated tracks with pile foundations driven deep into the ground. Just like the Trans-Alaska Pipeline, parts of the railway are also passively cooled with ammonia-based heat exchangers. That already sounds impressive, but believe us when we say that what comes next surpasses everything China has done before. Energy for the future. Very recently, in the middle of the barren expanse of China's Gobi Desert, a team of 750 scientists achieved what America's top nuclear physicists said was fantasy and impossible dream that defied the laws of physics and economics. They switched on the world's first commercially viable thorium molten salt reactor, and after some testing, it now runs perfectly. No meltdowns, no radiation leaks, no catastrophic failures. Just clean and virtually limitless energy, capable of powering entire cities for just pennies on the dollar. Even better, this reactor uses a fuel so abundant that China has enough buried in its soil to power the entire planet for the next 1,000 years. When the news broke, the silence from Washington was deafening. The U.S. Department of Energy, an institution that has spent billions on failed nuclear projects over the past 2 decades, quietly released a one-paragraph statement acknowledging China's achievement. MIT professors who had publicly mocked China's thorium ambitions began withdrawing their papers. Energy consultants who had built entire careers saying thorium reactors were 50 years away simply vanished from social media. And President Donald Trump's words he had said years earlier suddenly seemed prophetic. But their leaders are much smarter than ours, and we can't sustain ourselves. China, you go there today. Roads, bridges, schools, you've never seen anything like it. They have bridges that make the George Washington Bridge look small. Because here is the uncomfortable truth that no Western politician wants to admit. China didn't just build a better nuclear reactor. They built a technology that makes the entire American energy strategy look like a relic of the Stone Age, while the United States clings desperately to old uranium reactors that produce mountains of radioactive waste and still pose the constant risk of Chernobyl-style disasters. China has leaped straight into the future. But leaving politics aside, why does this matter to all of us? The energy crisis we pretended not to see. Because, contrary to what many would like to believe, the global energy crisis is not coming. It has already arrived. The signs have been there for a long time. In the winter of 2022, when Russian gas supplies were cut, Europe froze. The head of the International Energy Agency warned European countries to prepare contingency plans in case Russia completely shut off gas during the winter. And things aren't much better in the United States. California's power grid keeps failing every summer, precisely when air conditioners should be running at full blast. In developing countries across Africa and Asia, the situation is even worse. Gigatons of carbon dioxide are being dumped into an already suffocating atmosphere just so coal can be burned and the lights can stay on. And as we stumble through this swamp, the world population is expected to reach 10 billion by 2050. Each of those 10 billion people will need electricity to live. Unfortunately, it doesn't look like our traditional energy sources can keep up. Fossil fuels are cooking the planet in real time. The enormous areas of land that solar and wind energy require are not a sensible choice when you consider how intermittent they are. By blocking the annual flow of sediments and nutrients, and even destroying entire ecosystems, Hydroelectric plants are also too risky for us to depend on, and uranium-based nuclear energy. After what happened in Fukushima in 2011, when a tsunami caused a meltdown that irradiated hundreds of square miles of the Japanese coast, let's just say public opinion turned against nuclear power. Humanity needs something different, almost a miracle. We need an energy source that is clean, safe, abundant, and scalable. And that's where thorium comes in. But then the story becomes infuriating, especially if you are an American taxpayer. The United States actually invented thorium reactor technology, or at least was one of its main pioneers. In the 1960s, Oak Ridge National Laboratory in Tennessee built and operated the world's first molten salt reactor using thorium fuel. For about 4 years, the facility worked perfectly, and scientists called it the future of clean energy. But then, 1973 arrived, and the US government suddenly shut it down. The reason? You couldn't make nuclear weapons with thorium. The uranium reactors America was building could produce plutonium, the key ingredient for atomic bombs. At that time, the US was deep in the Cold War, and the arms race with the Soviet Union had reached its peak. The Pentagon wanted reactors that could do two things at once: generate electricity and produce weapons material. Thorium couldn't do that. So America abandoned it, buried the research, and poured trillions of dollars into uranium infrastructure. Over the next 50 years, thorium reactors were treated as a scientific curiosity interesting enough to write bold papers about, but too impractical to actually build. Western experts insisted the technical challenges were insurmountable. Corrosive molten salts would destroy any reactor vessel in a few months. Neutron radiation would shatter structural materials, and the byproduct tritium posed contamination risks that were impossible to control. The costs were too high, the timeline too long, and the chance of success too small. So thorium was pushed aside. But while American scientists were explaining why it couldn't be done, Chinese engineers were already rolling up their sleeves. In 2011, China's State Council approved a $3 billion United States research initiative called the Thorium Molten Salt Reactor Program. The goal? Build a working prototype by 2024. The international scientific community laughed. Energy analysts called it propaganda. Western media dismissed it as just another example of China's tendency to promise too much and deliver too little. But what those critics failed to understand was the Chinese approach to engineering. Because in China, the impossible is not a wall. It's just an inconvenient speed bump. While American companies were pressuring Congress to protect their investments in coal and uranium, China was pouring concrete in the Gobi Desert. And now, just 13 years later, the impossible dream has become reality. China's thorium reactor is not just working, it is almost perfect. In addition to producing clean energy with zero carbon emissions, it generates far less radioactive waste than most traditional reactors. The best part, it operates at atmospheric pressure, which means it physically cannot explode like Chernobyl or Fukushima. The United States had a 50-year head start on this technology and chose to abandon it. China took the designs, improved them, and built the future while America was still arguing about whether it was even possible. So how did they do it? What secrets are hidden inside that remote facility in the Gobi Desert? And what does this mean for the global balance of power in a future where energy is everything? But before we move on, it's important to get one thing straight. When America said thorium reactors were impossible, it wasn't just being dramatic. The fears came from real problems. There were 3 major engineering challenges that blocked the brightest minds in nuclear physics for more than half a century. And somehow, China overcame all of them. The first problem was heat. Imagine working with a liquid so corrosive, so reactive, that it eats through steel the way acid eats through paper. Heating that liquid to 1292 degrees Fahrenheit turns lead into vapor. That is the environment inside a thorium molten salt reactor. Traditional reactors use solid uranium pellets. But thorium reactors need a bubbling mixture of thorium dissolved in molten salts. So the liquid fuel flows continuously through the core, absorbing neutrons, generating heat, and producing energy. It sounds elegant, except for one detail. Molten fluoride salts are among the most corrosive substances known. At 1292 degrees Fahrenheit, they don't corrode metal, they destroy it. They penetrate the microscopic structure of metals, cause embrittlement, and trigger a process called tellurium cracking that can eat through reactor walls from the inside. In the 1960s at Oak Ridge, stainless steel lasted about 6 months before failing. Even the most advanced nickel superalloys of the time lasted only about 4 years. But a nuclear plant needs to operate at least 30 years to be viable. Replacing the core every 4 years would cost hundreds of millions of dollars. Financial suicide. American metallurgists tried everything. New alloys, ceramic coatings, exotic materials. Nothing worked in the long term. By the 1980s, the consensus was clear. There is no material on Earth that can survive 1292 degrees Fahrenheit molten salts for 3 decades. And the problems didn't stop there. The second hell was neutron radiation. Billions of neutrons constantly slam into everything inside the reactor. They lodge themselves in the atomic structure of the metal, creating microscopic defects. Over time, the metal becomes brittle. This is neutron embrittlement. After 40 years, even the strongest steel becomes as fragile as glass. And the third nightmare, tritium. Tritium is a rare isotope of hydrogen, produced when neutrons interact with lithium in the molten salt. It is extremely hard to contain. It behaves like normal hydrogen, can form radioactive water, and passes through metal walls like a ghost. This is tritium permeation. If it escaped, workers would be exposed, groundwater contaminated, and ecosystems poisoned. Even small amounts can make a facility uninhabitable for decades. This is not a theoretical possibility. Japan became a victim of this when it tried to build an experimental fusion reactor that produced tritium as a byproduct. Despite using triple-layer containment barriers and advanced ceramic coatings, tritium leakage exceeded safe limits within the first year of operation. The project was eventually abandoned after billions in losses. American nuclear engineers studied the Japanese failure in depth and concluded that containing tritium in a molten salt environment was an unsolvable problem. In other words, to build a working thorium molten salt reactor, you would have to solve three nearly impossible problems at the same time. First, invent a material that can survive 1,292 degrees Fahrenheit molten salt for decades. Then stop neutron radiation from destroying that material. And finally, contain tritium, a radioactive gas that slips through solid metal without leaving a trace. Oh, and you would still have to do all of this while keeping costs competitive with coal, natural gas, and traditional uranium reactors. In that scenario, you can't really blame everyone for giving up. But somehow, China managed to solve all of these problems completely and definitively. The main advantage they had was location. The reactor site, near the remote city of Wuwei, on the edge of the Gobi Desert, was chosen for several reasons. The first was total isolation. There, they could work with absolute focus. The region is also seismically stable, with no record of major earthquakes. In addition, there was access to underground aquifers, and if a catastrophic leak ever happened, radioactive contamination would remain confined to the desert. What's more, this thorium molten salt reactor does not need water. Most conventional nuclear plants depend on huge volumes of water for cooling, which makes them vulnerable to droughts and heat waves. The philosophy behind this multi-billion-dollar project was crystal clear. Choose the smartest people, give them unlimited resources, remove bureaucracy, and demand results. America had abandoned thorium research in the 1970s. Meanwhile, China was quietly translating every Oak Ridge report, studying every failure, and preparing to improve everything. And they did. To defeat corrosion, researchers redesigned the alloy atom by atom, adding titanium, increasing molybdenum, introducing niobium, and refining purity to an astonishing 99.97%. After 3 years testing thousands of samples under electron microscopes and spectrometers, they created a superalloy capable of surviving molten salt for more than 30 years. It reduced corrosion by 87% and virtually eliminated cracking. For the reactor's graphite moderator, instead of blocks, engineers filled the core with 60,000 graphite spheres coated with silicon carbide, each about the size of a tennis ball. Molten salt flows between them, creating a naturally self-regulating neutron environment. When the temperature rises, the salt expands, reduces neutron absorption, and slows the reaction without the need for control rods. In addition, a frozen safety plug melts if overheating occurs and drains the fuel into underground tanks. This design makes a core meltdown physically impossible. Before loading real fuel, scientists used a supercomputer to create a complete digital twin of the entire reactor system. They modeled every pipe, valve, weld, and component in extreme detail. They simulated cooling failures, earthquakes, and even deliberate attacks. In total, they ran 1 billion hours of virtual testing, the equivalent of about 114,000 years of operation. In doing so, they simulated virtually every possibility. The result was a fully functional reactor that, just a few weeks ago, entered full operation. But this is far from just a victory for China. It is a victory for the future of humanity. From a clean energy perspective, molten salt reactors using thorium fuel are attractive because they promise to solve several criticisms of traditional nuclear power. Operating at atmospheric pressure reduces the risk of high-pressure failures, while the liquid fuel can be drained into passive cooling tanks in emergencies, something seen as a major safety advantage. In addition, thorium is more abundant than uranium, and in a well-designed cycle, can generate less long-lived radioactive waste. Precisely one of the most politically sensitive aspects of nuclear energy today. China's decision to invest heavily in this technology is also a geopolitical signal. By leading with a working thorium molten salt reactor and tying it to a national strategy, Beijing positions itself as a standard setter for advanced nuclear designs that can be exported to energy-hungry partners in Asia, Africa, and the Middle East. And there's more. The rest of the world only woke up to this operating plant on November 21st. But China had been quietly working on it for decades. That can mean only one thing. Chinese engineers have been accumulating operational experience that other countries do not have. And this will translate into a commercial advantage when these reactors move from demonstration to large-scale deployment. If that happens, the thorium project will not just be a scientific experiment, but part of a broader effort to dominate the next generation of nuclear technologies, just as China already dominates solar panel manufacturing. But even if things do not move forward as expected, China deserves applause for at least taking this idea off the drawing board. Their philosophy of building first and improving later is something Western powers need to swallow their pride and start copying. Thank you for watching. See you next time.